In this lesson, we're going to talk about the conservation of momentum. So let's consider two balls that are about to collide. We have ball 1 going to the right and ball 2 going to the left. When they collide, we have forces we have the force of ball 1 on ball 2 and the force of ball 2 on ball 1. These are going to act like action-reaction pairs. So Newton's third law tells us that the force of ball 1 on ball 2 equals the force of ball 2 on ball 1 in the opposite direction. So we can write this as the force of 2 on 1 equals negative of the force of 1 on 2. Now, if you remember, this collision also has a variable of delta t, the time of the collision. Well, delta t for ball 1 is going to be the same as delta t for ball 2. So that means that the force of 2 on 1 times delta t equals negative the force of 1 on 2 times delta t. In other words, the impulse acting on ball 1 is equal to the negative of the impulse acting on ball 2. So recall that impulse is the change in momentum. So if the impulses on the two balls are equal and opposite, that means the change in momentum of ball 1 is equal and opposite the change in momentum of ball 2. This leads us to the law of conservation of momentum. And the law of conservation of momentum says that the total momentum, or P, of an isolated system is a constant. That is, the momentum before the collision is going to equal the total momentum before equals the total momentum after. Any interactions within the system are not going to change the system's total momentum. Mathematically, we write the law of conservation of momentum as initial momentum equals final momentum. This does not apply, the law of conservation does not apply if any outside forces are introduced to the system. So for example, if I have two balls collide and then friction acts on one of the balls, friction between the ball and the table, that's an external force, a non-conservative force. We can't include that in the law of conservation of momentum. However, there could be a special case if you wanted to include the table in your system. So let's say a ball rolls on a table and experiences friction with the table. You could still use conservation of momentum if you include the movement of the table, which would go backwards as a result of the friction, as part of your system. Now this is not typically going to be the case. Normally with conservation of momentum, we only consider interactions between the objects in our system, and we don't consider external forces like friction. So let's break the law of conservation of momentum into a little more detail. We have two balls that are colliding, and then they move apart from each other. So their initial total momentum equals their final total momentum. So we can break the P into parts for each ball. So initially, there's momentum of ball 1 and momentum of ball 2. So that means our initial momentum is the momentum initially of ball 1 plus the initial momentum of ball 2. At the end, our momentum includes the final momentum of ball 1 and the final momentum of ball 2. So we add our final momentum of ball 1 with our final momentum of ball 2. Now, what do each of these mean? Well, remember that momentum equals mass times velocity. So we can break this momentum, initial momentum of ball 1, to be the mass of ball 1 times the initial velocity of ball 1. And then the initial momentum of ball 2 is the mass of ball 2 times the initial velocity of ball 2. The momentum of the final momentum of ball 1 is its mass times its final velocity, and the final momentum of ball 2 is its mass times its final velocity. This equation right here, or some variation of it, this is what we use a lot in our conservation of momentum problems. We're looking for our total initial momentum to equal our total final momentum. There might be 3 balls, there might be 5 balls, but we're going to add all of their momentums on the left for initial momentum and all of their momentums on the right for final momentum. So let's do a problem. Two ice skaters, Fred and Francine, stand facing each other on frictionless ice. Francine has a mass of 45 kilograms. Fred has a mass of 80 kilograms. They both have an initial velocity, because they're just standing there, of 0 meters per second. They push off from each other. After the push, Francine moves at a speed of 2.2 meters per second. What is Fred's speed? This is what we're finding, Fred's final velocity. And we can find that using conservation of momentum. So first we say our initial momentum equals our final momentum. So initially we have Fred's initial momentum plus Francine's initial momentum equals Fred's final momentum plus Francine's final momentum. And now we're going to break it into more details. So the mass of Fred times his initial velocity plus the mass of Francine times her initial velocity equals his mass times his final velocity plus her mass times her final velocity. We plug in what we were given. His mass was 80 kilograms. He started at rest. Her mass is 45 kilograms. She started at rest. His mass is 80 kilograms. We don't know his final velocity. That's what we're finding. Her mass is 45 kilograms. And we know she ended at 2.2 meters per second. So now we can simplify this problem. It's 0 on the left equals 80 times Fred's final velocity plus 99 kilogram meters per second. And we can rearrange it and divide and find that Fred's final velocity is a negative 1.24 meters per second. The negative makes sense because they push off. He's moving to the left.